So what did we do yesterday? So yesterday we discussed the notion of quasi-isometry. So let me just remind you the definition. So a quasi-isometry is a map F between two metric spaces such that there are constants lambda and c with the following properties. So for any x primes in x, if I look at the distance of the image, then it is at most lambda times the distance from x to y up to an additive constant c, and it is at least 1 over lambda, the distance from x to y, minus c. And there was a second condition saying that the image was co-bounded. And this means that if you look at the balls centered at the images of radius c, then it covers the whole space. Okay, and the second, and what I sketched the proof of the Schwarz-Milnor lemma. That I call the fundamental lemma of geometry group theory that said that if G was acting on a proper geodesic space X, geometrically. So geometrically, let me remind you that it means that the action is by isometries, it is properly discontinuous and also co-compact. And in that case, we could conclude that one, G is finitely generated, and two, the evaluation map. So if you fix a base point x0 in your space X, the map which to G, an element of G with respect to a word distance, I associate the image of x0 under G. This is a quasi-isometry. Okay, so what I would like to, so this is a very, why is it that important? But for instance, I will just give one consequence. Is that if M is a compact Riemannian manifold, and I denote by M twiddle its universal covering. Then the fundamental group of M will be quasi-isometric. To M twiddle. Okay, so what does this mean? So this is something that I've set as an exercise. And so what is interesting there, it means that if, for instance, M is a hyperbolic Riemannian manifold or hyperbolic surface, then what happens is that the fundamental group will look like a Poincaré plane if it's a surface, and then we can try to use the fact that we have some hyperbolic geometry coming from the universal covering and try to transport it to the fundamental group and use methods from hyperbolic geometry to understand the way this fundamental group is structured. Okay, so it is really fundamental. And another consequence that is really important, so this is the first. The second is to say that two Cayley graphs, two locally finite Cayley graphs. Cayley graphs. Of a given group, of a finitely generated group, are quasi-isometric. Okay, so this means that as long as we establish properties that are invariant under quasi-isometry, then we obtain a property of the group that won't depend on the finite generating set that we fixed to start with. Okay? Is it fine up to now? Okay, so then I will switch to the next board and proceed now. So the questions that we are trying to answer are the following. So the basic questions. Is first, which properties, which algebraic properties. Okay, algebraic, I think because that's our main theme, but in general it could be geometric also. Which properties are invariant under quasi-isometry? And what can be said of two quasi-isometric groups? So what do I mean by two groups are quasi-isometric? It means that of two finitely generated groups. So what I mean is that you pick any Cayley graph of each group, and you just assume that they are quasi-isometric. And because it does not depend on the Cayley graph, we can speak about the quasi-isometric class of a given group, because it means that we are looking at all the metric spaces that are quasi-isometric to one or any locally finite Cayley graph. What I mean by locally finite, it means that I only consider finite generating sets. So in this case, we have finitely many edges. Okay? So this is what we are trying to do to understand algebra. So in the time that I have left, I would like to present you three quasi-isometric invariants. Actually, being a hyperbolic group, I don't know if Indira had time to define it in the beginning of her course, but this is also a quasi-isometric property. But this you'll see so later on. We should interview it. Questions? Okay, so if not, I continue. So the first quasi-isometric property is the notion of finite presentability. Okay, so let me fix some notation. So G is a group. And I fix a subset A in G. So when I put it into brackets, single brackets A, this is the group, the subgroup, oops. Generated by A. So this is the intersection of all the subgroups of G that contains A, all the, okay. And now I will define something else. When I put a double bracket, this means that it is the smallest normal subgroup in other words, it is the intersection of all the normal subgroups that contain A, or what we can say it is the normal closure Okay, so let me remind you that the other day I said that when we had a finitely generated group with a finite generating set, we could consider the morphism from the free group over the alphabet S into G, which just consists in taking a word in S, we associate the element that is obtained by seeing them as elements of G and making the product. And so what we know is that the kernel of phi is a normal subgroup and moreover, what I had told you is that the group G was the quotient of the free group over the kernel. Okay? So now I will say that G is finitely presented if there exists a finite set that we call R into it is a subset of the free group over S, such that the kernel of phi is a normal closure of R. Okay. In this case, we write G, this is a notation. Huh? And then you put a vertical line, so S for the generating set, and then the set R, meaning that these are the words that will give you the identity when you map it under phi, because it is in the kernel. So every word that are made out of letters of R or any conjugate will be mapped to the identity, to a trivial element in G. So this means that this is the quotient of the free group over S by the normal closure of all the words. And the elements are, why do I use this letter? It's because it stands for what is called a relation. Okay. And so there are two things. So is the definition clear, or do you have a question or something? Okay, I cannot see the chat. Maybe on this other computer I can. Ah, okay, so there are messages. Maybe I should put them. I know, it's just in the question. Okay, good. Okay, so now let me, if you have no questions, maybe some examples in the next screen. So the basic example is, so for instance, oops, sorry. So for instance, the cyclic group Z is generated by one element and you have no relation. Okay. If you look at Z2, then you have the standard basis is to have two generators, and the main property is that they commute. So AB, so it means that the commutator is, belongs to the kernel. And if you want a finite group, for instance, Z over NZ, this is cyclic groups are generated by only one element, and the main property is that A to the N is trivial. Is that clear up to now? Okay, so there are two results I want to state about finite presentability. And for the free groups, it's exactly like Z. There is nothing to. So if I look at f of s, so it will be S1 up to Sk if I have k elements. And the same here, there's no relations. And that's why the K graph is a tree, by the way. Because you see, each time you have a relation, it means that you have a loop that goes back to the identity if you look at the Kelly graph with respect to AB. So I start with, let's take some colors. I start with A, then I go up with B, I come back with A inverse, and then I come back with B inverse, and I go back to the point I started. So every time you have a vertex, you do AB, A minus 1, B minus 1, you go back. Okay, so the first theorem is a way of characterizing, it's a little bit like the Schwarz-Milner lemma. It gives you a characterization, a geometric characterization of to be finitely presented, saying that this property that is purely algebraic, saying that you can find a finite set whose the normal closure of which will give you the kernel of my morphism phi. Can be read from the way we can make act, we can let the group act on a space. So just, I don't want to be mistaken, so I'll just check my notes. Okay. So a finite group G is finitely presented if and only if it admits a geometric action. Oops, geometry, sorry. Geometric action on simply connected geodesic and proper metric space. Okay. Yes. Okay. So this is, you see, so the assumption is a little stronger because not only do we assume that we have a geometric action on a geodesic proper metric space, but that space is also simply connected. And from there, we can read the finite presentability. Yes. Okay. And the second theorem is the fact that let G and H be two finitely generated groups that are quasi-isometric. So the G has finite presentation if and only if H also. Okay, so this is a property that is invariant under quasi-isometry. Okay. Any questions about that? Maybe I'll check if you ask questions in the chat. Please, you can, if you want, you can use the microphone if you want to ask a question. Feel free. An example of non-abelian groups which can be presented Oh, yes, yes, of course. Otherwise, it would be. So this is a good example. So the free group on two generators is an example, but also the surface groups. If you look at the surface of genus G, so this means that you have something like this, and you have G angles. Then presentation for the fundamental group. So you have two G generators. So usually we call them A1, B1, A2, B2, up to AG, BG. And then the relation is the product of the commutators A1 and B1 times A2, B2, up to AG, BG. The identity. So this is also basic examples of non-abelian finitely presented groups. So actually, all the every Riemannian manifold, their fundamental group is always finitely presented because the universal covering is simply connected. And one of the exercises I would like to do, that I hope we'll have time to do, is that the action of the group on its the fundamental group of the manifold on its universal covering is also geometric. So we are exactly in the setting of this theorem. And therefore, fundamental groups, most of them are non-abelian. Are there other questions? But the free product is a great example. Okay, good. So then, if there are no other, I would like to present another QI invariant. So in my notes, so I have 5 minutes. I don't know. So I think I will motivate one sheet of exercises, and then I go in tomorrow. I talk about a third example. So the second is the notion of volume growth. Of groups. Okay, so you let G be finitely generated with S a finite generating set. Okay, and so what you can do, you call V sub S of N is the number of elements G of cardinality at most N. Okay. So there's a whole sheet of exercises around that. And so this is a fundamental property, notion of finitely generated groups. And so the volume entropy or the volume growth are denoted by V sub S. It is the limit as n goes to infinity of 1 over n log of Vsn. So it turns out that this limit always exists because this sequence is a sub-multiplicative. So this is in the exercise. So everything is, I have a whole sheet of exercises called growth of groups, I think, of growth. And it's really devoted to study the basic properties of this. So I just want to tell a little bit about it before you start working on it. And so, so the volume, the size of a ball, of course, it depends on the generating set. Here also, it can depend also, the limit depends. What does not depend on the limit is the fact that it is positive or not. So, Vs positive is a QI invariant. meaning that if you change generating set, and if for the one it is positive, it is positive for the other. And also, if you take a quasi-isometry group, they will be simultaneously positive or not. And in this case, we say that G has exponential growth. And so this, we have many examples about that. For instance, the free groups, the surface groups. Okay, so if Vs is 0, so this is also a quasi-isometric invariant, but then maybe the growth is smaller than a polynomial, does not grow faster than a polynomial in N. And then we say that G has polynomial growth. And this is also a property that is invariant of the quasi-isometries. And there I have to say a theorem that was one of the cornerstone of the theory. So it's a theorem published in 81 or 2, I forgot, of Gromov, that characterizes polynomial growth groups by an algebraic property. So G has polynomial growth if and only if G admits finite index nilpotent subgroup. So being nilpotent is a purely algebraic notion, and to have polynomial growth a priori is a geometric notion because we are counting elements in balls and just looking at how it grows, how they grow. Okay, so this really put back it's really started the systematic study of geometry group theory. And the last thing I would like to say about that is that we also have so examples, of course, well, ZK, for instance, and any potent group by definition. So I don't want to define this because in any case, you'll have a course on that in the second week by Touquet. And then we have groups of intermediate growth. So this means that they are not exponential. The Vs is 0, the volume entropy is 0, and also, but it grows faster than any polynomial. And so the existence of such groups is due to Grigorchuk, and this is rather recent, and it's in the 80s. I don't remember which year, but it's in the list of reference that I put on the Zoom. Okay, so we have, in some sense, four classes of groups. So if the sequence of sizes of balls is finite, is bounded, then it means that the group is finite. After that, it grows at least linearly, so polynomially, and we get groups of polynomial growth. And then it can be faster than any polynomial, but not exponential. And then we have these groups of intermediate growth that are still very mysterious. And then we have most of the groups that we are studying will have exponential growth. For instance, hyperbolic groups, they all have exponential growth. And you have some amenable groups that have also exponential growth, but not all of them. Well, there are many interesting groups like that.